Okay, so I want to tell you about the question of simulating Hamiltonians by other Hamiltonians. And this is joint work with Leo Zhu, a student of Lukin from Harvard. Okay, so basically this goes back to Zhonghang remark about the fact that we want the ground states, or maybe the gap, and that's it. Now, surprisingly, we looked for formal definitions of this, and we didn't actually find any place where this was rigorously defined, like what is the goal and what's the formalism, etc. So we had to define it. So I'll show you the definition of this, of what I mean by one Hamiltonian simulating another, actually gap simulating another. So H is sort of simulated by H tilde, which works on some Hilbert space tensor. I have overused H. I don't know, C tensor C ancilla. And basically what we want to do is we want that this thing will characterize the properties of the ground state of this thing. And the question, once we define it correctly, is what are the resources required to do that? I should say that in things like perturbative gadgets and stuff like that, what you actually do is simulate the whole thing. So I don't want that. So if I want to just simulate the ground state, the question is what are the resources required? And one question which is very reasonable to ask is, can I remove interactions from the interaction graph? I have here some n qubits with some interaction graph. And I want to maybe sparsify the graph. I want to do something to this graph, make it simpler. I want to remove edges. I want to make the degree small. Maybe the degree is very large. I want to dilute it. I want to do something like sparsify the graph. I'm using this very vaguely. So I'm going to define this notion, and then I'm going to prove, ask the question of whether we can always do this and answer and prove a theorem. I mean, tell you about a theorem that says no in the quantum case, and in the classical case, we know that it will be possible. So this will be an example where such a task is impossible in the quantum case. For a particular Hamiltonian. So what's the definition, first of all? Okay, so we have a Hamiltonian, we have some spectrum, and there's a gap here. And we want the new Hamiltonian to act on another space such that the spectral gap is preserved. And such that, so there are two different definitions, and I leave you to think for a moment what will be the stronger one. So the first one is that the projector on this ground space minus P tensor some projector on the ancilla of the some subspace of the ancilla additional qubits, this is less than epsilon. That's one definition. And the other definition is P tilde minus P tensor 1 ancilla times P tilde, that's less than delta. Which is stronger? Okay, I'll tell you. This means this is much stronger. This sort of preserves the coherence in the subspace, whereas this just tells you that the projection of the ground space of the new Hamiltonian, when you ignore the ancilla and you consider just the support on the original space, it is contained in the original ground space. So that's much weaker. That's sort of incoherent. That's coherent. But when there is a unique ground state, they turn out to be the same. So lemma epsilon is O of delta, or something like that. This is, by the way, the straightforward thing gives me a factor of the dimension, but you can get rid of it, which is important. And then what we want to do is we want to gap simulate a Hamiltonian by a Hamiltonian with many less with much less degree, with a constant degree. And theorem is that there exists a Hamiltonian such that there is no gap simulation like that with a constant degree, as long as the interaction strength is constant, and no matter how many terms we add. Okay, so that means that you cannot do degree reduction in the quantum world, whereas in the classical world you can do degree reduction. If you don't care about coherence, you can always replace a set of constraints by a set of constraints with a constant degree in a way which is very simple, by adding an ancilla, essentially, by adding more bits. Okay, that's it, I think.
Questions?
Yeah, can you say a word about how you show this, or what?
Yeah, thank you. So how do I show this? So first of all, there are two Hamiltonians that are counterexamples. One is classical Hamiltonian, which gives a counterexample to trying to do it coherently, because it's spectral. It doesn't have a unique ground space. And then actually you have to work a little bit harder for the stronger result. The way you show this is that basically, if you want to show this with epsilon equals 0, that's much easier, because what you show is that you look at the ground state. So I won't write the Hamiltonians, but the ground states are simple. The ground states are just the sum. Actually, the first Hamiltonian is easy. HA is just, it requires that there are no pairs of ones. So the ground space is spanned by all 0 string and just a single 1. And then you somehow look at the state, which is the sum over all strings with just a single 1. And the Hamiltonian somehow needs to know that there are no far away ones. And you write down the energy, you do some trick, and because you can move from one to another locally, it works. But then the epsilon gives a lot of problem, because a little bit of an error in the state could give you a lot of energy. So you have to use Hastings-Coma decay of correlation. So you have to modify a little bit Hastings-Coma decay of correlation, and then sort of get to a contradiction not by the energy but by the correlation.
So here you showed that you cannot really reduce the number of to lower the degree of the interaction graph. But I guess the motivating example was to construct a Hamiltonian which has smaller norm. Whereas
no, I didn't want to construct I didn't care about the norm. I really cared. So this comes up in various situations. For example, people here are working to come up with examples of Hamiltonians related to the area law with constant degree. I mean, this comes up in various contexts. So it's not necessarily because of reducing the norm. It's really asking, can I have some properties of the ground state exhibited by a Hamiltonian with some restrictions?
But you didn't consider the case that somehow chopping of high energy levels, because for simulation usually the problem is that if the Hamiltonian has too large norm, it's harder to simulate, and you only care about
we actually did. We call this dilution of the Hamiltonian, and there the problems are much harder. We cannot prove, this is an information theoretical impossibility result. There we cannot prove an information theoretical result, but we can prove a computational. Under some computational assumption, this is impossible, even classically in the general case. But we don't know this is an open problem. By the way, this is related. We also show some relations to impossibility of degree reduction in the context of quantum PCP, but it's not a direct impossibility in the context of quantum PCP because of the difference between promise gap and spectral gap. That was for the experts.
Okay, let's thank you then.
The USB-C. Here.
Oh,
Just wait.
okay, our next speaker is.
Okay, hi. I'm going to talk about some joint work with Umesh and Henry on some circuit lower bounds and some error correcting codes. So let's just start off with two different notions of error entanglement, and let's see how they're similar. So consider a Hamiltonian local, and let's just say it's frustration-free for a second. So on the left, in orange, well, let's say we're going to consider an idea of low energy, which is just any state whose energy relative to this Hamiltonian is some smaller than some epsilon fraction. And on the right, we have this notion of low error, which is any state which up to some epsilon n of the qubits, it looks like a ground state. As in, you take a ground state, you apply some error, and you see what happens. And now a good question to ask is, are the complexities of these two things related? And what can we say about them? Well, first one you can say is that this low error implies low energy, assuming a reasonable constraint on your Hamiltonian, which is that each particle acts in a bounded number of terms, then low error implies low energy. So the complexity of a low error state will be that of a low energy. But it still stands, what is the complexity of these low energy states? As in, even if the Hamiltonian's ground state has high circuit complexity, as in it takes a big circuit to build it, does that say anything about its low energy states or not? Okay, one could formalize this, and this was formalized in what this NLTS conjecture, no low trivial states conjecture, which says that there should be a family of Hamiltonians for which all states under low energy cannot be generated by constant depth circuits. And this really is saying, okay, for low energy states, can we classify its complexity? And this is actually a very natural and interesting problem to consider, particularly because of its relation to the quantum PCP conjecture. And it's an implication under a very plausible assumption, NP does not equal QMA. Okay, so there is this conjecture, and one might say, is there a similar conjecture for a low error state? There is, and it was proved by Eldar and Harrow that there exists a family of local Hamiltonians such that any low error state, low error in the same context that I did a slide ago, that some fraction of the qubits get affected, these cannot be generated by constant depth circuits. So what we prove in this paper is we prove a simple 1D construction of one of these n-lets Hamiltonians that is not NLTS, which is the one on the left. And the idea is this construction is it's a Feynman-Kitaev clock Hamiltonian of a cat state, which 2 presentations ago we saw must have log circuit complexity. And we can show that this Feynman-Kitaev clock construction also contains this property. Okay. So it tells us something very particular, that these two notions are actually fundamentally different. The low energy definition, it seems to be the correct definition for quantum PCPs and entanglement at room temperature. A low error one is, it's the right notion for error correcting codes and physical processes, these sort of things. Anything where the error acts per qubit by qubit and doesn't affect the whole state at one time. And actually, as a simple consequence of this and us building this NLETS Hamiltonian, we saw that because of this error model is so specific, we were able to create a different type of error correcting code, which we called a quantum low weight check code, that has really good properties in a lot of different ways. It has linear rate and distance, and each of the terms is local. It acts only on a constant number of things. I think we can do it with 7. And furthermore, well, we actually can't construct this exactly, but an approximate version. And it's also conjectured if there are other types of error correcting codes. And what one might take away from this is that a computational perspective on these error correction might be helpful in building either of these two other types.
Yeah.
That's all.
Yeah, I have a question about the quantum low-weight codes.
Uh-huh.
So if you have really a quantum LDPC code, you can imagine, really running error correction over many rounds that you encode some state and some errors occur, you correct them, those in the distance, more errors, you correct them, more errors, you correct them. And I was just wondering with this kind of approximate code you have, where they're like not really stabilizers, as I understand it, but stabilizers.
Yeah,
Does it still work as a quantum memory, or is it somehow weaker than a true LDPC code that have stabilizers?
So actually the construction we have is a little bit interesting. It probabilistically fails in the error correction. So it'll preserve the state exactly with inverse 1 minus inverse poly probability, but with inverse probability you'll fail kind of arbitrarily. So I think in that sense you can.
It fails undetectably or?
Undetectably, yeah.
You were also talking about the fact that the energy gap is much smaller here than usual, no?
Yeah, the spectral gap of this code is inverse poly versus a stabilizer code has.
So measuring that you're out of it is also becomes.
Yeah, yeah. This is a code in the sense that there is a non-commuting Hamiltonian which defines this ground space, which has, with small spectral gap. That's how we have it defined.
This is the error correction.
Yeah.
Yeah, so how should I interpret this, the fact that, so if the spectral gap was exponentially small, would you be happy? Like, how should we interpret the fact that the spectral gap is smaller than in usual?
Well, exponentially small gap is actually kind of tricky. Elizabeth and Henry and I were thinking about this for a while. Because if the gap is exponentially small, how are you going to measure it? Are you going to measure terms one after another, or which terms? It's sort of saying you're violating some tiny term by such a small fraction, or maybe all of them slightly.
Should we view these as codes for all purposes, or like are they honest to goodness codes?
I frankly don't know. That's a good question. Maybe.
We don't know.
I wouldn't think so. I think it's.
I think the gap is important. You need to say something about the gap.
I wouldn't think so.
You wouldn't think so.
So like an error correction circuit for this couldn't just measure stabilizer. It would have to really like do a quantum phase estimation.
Yeah, no, definitely.
It's derived from like a stabilizer code, but really to correct it, you'd have to like measure all the stabilizers which act on like a constant fraction of the qubits. I think maybe one way of looking at it is that when you're thinking about constructing codes in a very general sense, like as ground spaces are local Hamiltonians, the gap is something that's important.
Yeah.
Okay, let's thank you, Megan.
I think it's awesome.
Next speaker is Homomorphic.
So I'm going to talk about a result that was mentioned in Scott's talk on Tuesday. So it's a result on certified randomness expansion. I managed to forget the title of the paper on the archive. So this is on the archive. It's a different title, but it's the same authors. So this is with Zvika Bakursky, Paul Cristiano, Urmila Mahadev, Umesh Vazrani, and myself. And so I want to tell you about it because it's based on what I find is a very simple, very elegant idea. It's kind of an old idea in quantum information that turns out to be surprisingly powerful. So the same idea is going to show up in this brief presentation. Also, Urmila right afterwards is going to show you how to build quantum homomorphic encryption using that same idea. Then I think Zvika might say something about it later, and then tomorrow morning again you'll see it. So I'll try to keep it simple here. So let me first describe the setup. So the setup is going to be like this. So you have this quantum device. In general, it's an arbitrary machine, and then there's a verifier, and my verifier is a classical polynomial time machine that interacts with the device. And the goal is to get random bits out of that device. And so we can think of this as, generating randomness, and Scott also reminded us of this in his talk, is one of the simplest things that a quantum computer can do in principle. And so can we do it in a way that's verifiable, right? So I'm going to interact classically and try to get randomness out of this device. And so the simple idea is that what I'm going to try to achieve is, the goal is to force the device to prepare a plus state and measure in the computational basis. How do we do this if we can't look inside and see what the state is, right? So there's going to be one assumption. This is the computational assumption. I'm not going to describe it precisely. It's a bit more subtle, but the way you can think of it is just let's assume that there is a 2-to-1 collision-resistant hash function. Okay, it needs more properties. It's a bit more complicated, but you can just think of it in this way. So I'll take a function f that goes from n bits, let's say, to n minus 1 bits. So it's 2-to-1, and it's collision-resistant, in some sense. But we can instantiate exactly what we need based on learning of errors, right? So for example, the computational assumption is learning of errors. So that's the assumption, and let me describe how we're going to use that assumption to design a protocol to verify randomness generation from that device. So here's the protocol. It's very simple, so I'll put maybe the device on the left and the verifier on the right. So what I ask the device to do, of course, the device does what it wants. The only thing I control is the verifier. So this device should prepare a uniform superposition over all inputs and evaluate the function on that uniform superposition. And then it's supposed to measure the evaluation of the function. This is going to get some value y, that's an n minus 1 bit string, and report that value y to the verifier. So from the point of view of the verifier, of course, I know nothing of this. The only thing that I see is that I get a y, right? And I'm going to issue a challenge to this device, and there's one of two possible challenges. So maybe let me separate them. This is like or, so there's going to be two different things that can happen. So if I send a challenge 0, it kind of means, well, give me a random bit. So let me be a little bit more precise. So once the device has measured a y, because this function is 2-to-1, that register should be projected on something that looks exactly like a plus state, right? Except that it's in a basis that's 2 preimages of this y. And so when I issue the challenge 0, I'm asking the device to justify that it has at least one preimage to this image y. Right? So what it should do is just measure this and obtain x0 or x1. And then I'm going to check that this is a valid preimage. Okay? So that's the part where basically, I had a convoluted way to tell this device, why don't you prepare a plus state? The way you prepared it is this way and then measuring the image, but that's the plus state. And then I'm telling it, please measure the plus state and tell me the outcome, right? You can observe that up to that point, a classical deterministic device can solve this problem, can follow my protocol up to there without any difficulty, just by doing things the other way around, by first choosing an x, some fixed x, computing f of x, reporting that at y, and then returning the fixed x, right? So the important part is the test that you're going to play here with some probability. This is where you're going to use some randomness. So this is challenge equals 1. And then I want to ask it, well, prove to me that the way you got this y was by creating this superposition. So prove to me that at that point you have this. And so then I'm really asking the device to do the one thing that quantum computers can do that's different from measuring in a computational basis, which is measuring the Hadamard basis, right? So what the device should do is apply a Fourier transform over Z2 and then measure. And if it does that, it's going to get an equation in the parity of x0 and x1. So it's going to return to me an m such that m inner product x0 plus x1 equals 0. Measure Hadamard. Okay. And so the result is that any device that succeeds in the protocol with non-negligible probability, where that test is executed with small constant probability, must be randomness generating. And so the proof of that is a little bit delicate. The natural thing to attempt is a rewinding kind of attempt to say, well, if you can succeed here and you can succeed there, then you're able to find preimage and an equation in these preimages, and so that should somehow, you're not directly violating collision resistance, but, well, you build your way there. So I guess I'll stop here. Thanks. Yeah.
You can find both privileges, right?
Oh yeah, I forgot. So that's one of the additional assumptions. This needs to be a trapdoor function. And the verification here involves using the trapdoor. So we have an LWE basis. Yeah, thanks.
Any other questions? Okay.
Which connector?
Okay, our next speaker is Arnul Mahadev.
I'll be talking about classical homomorphic encryption for quantum circuits. So in this setting, if you have a quantum computer on the cloud and you'd like to delegate a computation to it, can you delegate it while maintaining privacy? So you only have a classical computer and you would like the quantum computer to run a computation on your data without learning anything about the data. This question has been well studied classically and is called classical homomorphic encryption. In the classical setting, the client would like to delegate a computation to a server, and the client is a weak machine while the server is much more powerful. To do so, the client sends over encrypted data, and the server should be able to compute on the encrypted data. This was first shown to be possible by Craig Gentry in 2008. This question has also been well studied in the quantum world, and it was first introduced by in a paper by Anne Broadbent and Stacy Jeffrey in 2014. Since then, there has been one protocol satisfying the definition of quantum homomorphic encryption, and this resulted in the first scheme for blind delegation of quantum computation with only one round of interaction. So all previous schemes before this required polynomially many rounds of interaction for a quantum machine to blindly delegate a computation. The disadvantage of this scheme is that quantum evaluation keys are required. So each time the quantum client wants to delegate a computation, he needs to generate a quantum evaluation key which helps the server to run the computation. The problem is that quantum keys are not reusable. So the quantum client needs to run a polynomial time quantum computation each time he wishes to delegate a polynomial time quantum computation. The key workaround here would be if we could have a classical client instead of a quantum client. So here you have a classical machine who wants to delegate a quantum computation. So he's only sending over classical encryptions, and the quantum machine should be able to compute a quantum circuit on top of a classical encryption. In this setting, the client is much weaker than the server because he's classical versus quantum, and the keys can naturally be reused because they're classical keys. I'm showing that this is possible assuming the quantum hardness of the learning with errors problem. Okay, this question intuitively reduces to the server's ability to extract a bit S from a classical encryption and store it in superposition. This is because he's only getting classically encrypted data, but he needs to somehow compute with it in superposition. So he needs to extract the classically encrypted bit and put it in superposition. And that's what I'm trying to show here. So here the server has a classically encrypted bit, and he's somehow taking out the classically encrypted bit and putting it in his superposition. And there's these extra parameters, and you can think of this as randomness. So mu0 is a random bit, and r0 and r1 are random strings. And they serve a purpose here because if they were not there, then the server is just storing S in superposition, and this would violate the security of the classical encryption schemes. So this extra randomness does have to be present. Now, what I'll show next is that if this classical encryption is a trapdoor claw-free function, this is a function that Thomas just mentioned as a 2-to-1 collision resistant function, yeah, then this conversion is easy. Okay, so let me first remind you what trapdoor claw-free functions are. So here I'm just splitting the domain. So the first part is a bit, and then you have the rest of the domain. And the first thing is that it's 2 to 1. And the second important property is that it's hard to find a claw, which is a pair of overlapping pre-images. So any pair of overlapping pre-images should be hard to find. And the extra property I require here is that each claw hides a bit s. So now this function f is a classical encryption of the bit s, because you're hiding the bit s in a claw, and it's difficult to find a claw. Now, given this classical encryption, it's pretty easy to convert the encryption into a superposition. And the way the quantum machine does this is he just, like Thomas mentioned, he can create a superposition over a claw. And since mu0 plus mu1 equals s, you immediately get a superposition like this. So the server succeeded in converting a classical encryption and storing the bit in superposition. Okay, so what I've shown is that if an encryption scheme, if a classical encryption scheme has a trapdoor claw-free structure, then it can be used to evaluate quantum circuits because it can be used to take a bit and convert it and store it in superposition. To get a quantum homomorphic encryption scheme, I need to make this more general. So I need to show that given an encryption under a classical homomorphic encryption scheme, I can convert it into this TCF structure. And I can do that if the classical homomorphic encryption scheme satisfies certain properties. So cryptographers might know these properties. So if they satisfy randomness recovery and circuit privacy, then an encryption under a classical homomorphic encryption scheme can be converted to this trapdoor claw-free function. And then that classical homomorphic encryption scheme can use to evaluate quantum circuits homomorphically. So I call classical homomorphic encryption schemes which satisfy these properties quantum capable, and those schemes can be used for quantum circuits. And that's all. Yes?
So just to make sure I have it straight, is this like solving a complementary problem to your other work that you'll talk about tomorrow, I guess, that one gives verifiability and the other one gives blindness, but both under basically the same kind of cryptographic assumptions?
Yeah, it is. So verifiability requires a bit of a more complicated function, but it reduces to the same assumption. And I guess they're not quite complementary because in previous settings, they always came hand in hand. But I didn't. In this setting, I don't think they come hand in hand because I don't think this implies verifiability.
But you could just use both of them at once.
Yes, you can do that. Yeah. Yes.
So I guess the same question also for Thomas. So the overhead for the server to do actually this would be that you have to create this n qubit state and which for like n1024 at least, or something that makes it secure for the LWE.
I think maybe Umesh and Thomas have better numbers for what, like for security of LWE.
Yeah, it's basically the size of the LWE
basically
number of equations.
Key somehow.
So, no, it's even a bit bigger than the keys. So.
Okay.
Yeah, it's been, yeah.
And how robust are you in doing this with some errors somehow? So if I cannot, I mean, if I am a server at IBM, there's no way I can do this. But if I can roughly do this, could I?
Depends what your model is. So what you're doing is you're just computing linear equation. You're not inverting, computing. So it's you're doing a matrix vector multiplication in superposition. So you have a superposition of all vectors. The matrix is fixed and hardwired, and so you have sum over x, and A is fixed, and you want to compute sum over x.
I'm just trying to understand. Can I verify a 100-qubit noisy computer that IBM would put on the cloud somehow? That's my question.
It depends how noisy it is.
So even if it's not noisy,
well, you'd have a certain amount of bit security of LWE, right? So I think you could optimize this, and you could get maybe wouldn't it be reasonable to get, let's say, maybe 20-bit security or something? And so that's already timed to the 20, and it's not cryptographically secure, but it, you know, I mean, you would get to the kind of like the kind of thing that's going on.
So you need bigger somehow if you really want the good security. Like cryptographic security is like 2 to the 100.
I mean, if you have 20 qubits, you're not going to solve it.
I think the issue is whether one can do this in low enough depth, and we haven't yet explored it. It's plausible.
But you mean it's not?
Also with errors.
And also with errors, that's the thing.
Also with
Yes.
errors.
No, but you know,
But
if we go with what Misha told us about 100 qubits.
Oh, but
yeah, you know, then it may fit into that.
Yes, just
so it's plausible, but we haven't checked.
Just to say that what Misha, what he has is near his neighbors atoms, not a complete graph like the ions.
Yeah, but
so the depth goes.
Okay, maybe let's on to the next talk. So let's make a move. So our next talk is Tongyang Li.
Hi everyone. So today I'm going to talk about quantum algorithms for learning distributions. Okay, so first, what is the motivation of this topic? So I think the most important part, if you want to discuss about machine learning, is data. Yeah, so it's like basically the data is the core of machine learning, and every power of the machine learning just comes off the clever way of using data. So speaking of the data, one thing that is very interesting is that the data is of course not random, and usually in many real applications, the data are just like drawn from a certain distribution. And actually, in many machine learning tasks, a main question to ask here is just to that, what can we say about this distribution that underlying these data, like basically how we can say about a distribution using the sample of it. So I think this is a very natural question that is addressed in classical machine learning theory. And in particular, I think people notice a very important phenomenon that if you take enough samples, then you can basically have a very good understanding what is the underlying distribution is. But I think for many interesting cases, you don't need to really cost that much. It is like basically, you can always brute forcefully tomograph a distribution. But basically, can we say learn more about, for instance, for some specific properties, can we learn this kind of properties more efficiently? So by the property here, I mean, for instance, something very interesting related to the distribution, such as the entropy of the distribution, or maybe, for instance, the momentum of the distribution, or distances between the distributions, etc. So here, I think due to the time limitation, I won't talk too much about like specific examples. Maybe let's only focus on one specific case, that is the learnability of entropies. Or maybe let me just quickly recap what is the definition of entropies. For instance, the definition of Shannon entropy is just the summation of minus p times log p. And there is a natural generalization of the Shannon entropy called the Renyi entropy with a certain parameter alpha, denoted by h alpha p, which just contains the Shannon entropy as a special case when alpha equals to 1, and when alpha not equals to 1, it's like a alpha power sum, a normalized kind of alpha power sum. So a math question here to ask is that, for instance, if I give access to sample from a certain distribution, using how many number of samples can you determine the Shannon entropy HP or the alpha Renyi entropy H alpha P within a certain reasonable error epsilon and with high success probability, say at least 2/3. So this is a very well-studied problem in classical information theory and machine learning. And I think as a quantum computing person, a very natural question here to ask is there any quantum speedup for estimating Shannon and Renyi entropies? So here I won't give like the really very complicated complexity bounds here, but maybe let me show a figure here. So the figure here, basically the green represents classical tag bounds, and also I use the right and the blue for the quantum upper and lower bounds. So like a take-home message here is that basically we get tag bounds for the case where for the Shannon entropy case, and also for the special case of the 0 and the 2 Renyi entropy estimation. And also this is not like our own work, but with the help of the previous work by Ben Kothari and Thaler. And also on the other hand, basically we show a good quantum algorithm that can give provable guarantees for all the alpha, that is in general for Renyi entropy estimation. And basically for the Shannon entropy case, we get a quadratic speedup for estimating it. And in general, for Renyi entropy estimation, we also get a speedup, but the speedup is somewhat slower than quadratic. Yeah, so like a very brief like roadmap of the techniques is that we use something mature from previous quantum algorithms, such that the learning graph, like the quantum counting, or maybe also this kind of simulated annealing and Chebyshev cooling idea. And basically we use this kind of ideas to give good estimation of entropy for different ranges of alpha. Yeah, so this is like a very brief story about entropy estimation, but I think I probably omit one important thing. What is the quantum model here? So the quantum model here I'm introducing is a classical distribution with coherent query access. That is basically, we'll assume a certain unitary OP here, so that basically maps the quantum state as 0 to the state as OPS. Or in other words, as a very specific example here, with a probability distribution on 3 elements and with the value of the distribution to be 1, 6, 2, 6, and 3, 6 respectively, then basically one possible OP is this one. So this is the model we used for the entropy estimation project, and there are also other possible models that we can study. For instance, you can consider like a classical distribution stored in a state, and basically for this example, we can consider like a state as this, which is a superposition of 1, 2, and 3. So this is like, we consider different perspectives of learning the states. And basically, this is like still focused on classical distributions. And we can also focus on the quantum case, for instance, like this kind of block encoding that has been well discussed in yesterday's talks. And also, you can also just assume that you got a copy of density matrix. And actually, I have an ongoing project with Andrej Gillian that basically we study sample complexity under these quantum models and study important properties like the L1 norm, L2 norm, also the entropy or the independence between distributions, etc. So maybe a quick summary and maybe like discuss about some open questions for future discussion collaborations is that, for instance, is it like in general for the LCU technique or the block encoding technique, can we estimate a general smooth function of a probability distribution? And also regarding to classically machine learning literatures, people not only like for learning distribution, they focus on parameters, they can also like for learning properties, they can also like learning parameters and also learning the shape of the distribution, like what if your distribution is Gaussian and its expectation variance, and whether the distribution has an interesting shape. Yeah, so that's basically ends my talk, and thanks. So any questions?
Yes. This was one of the things in your paper.
Yes, yes. So the Chebyshev cooling is that my algorithm enjoys a property that basically we define a certain random variable. Its expectation is close to the entropy that we want. And its variance is somewhat bounded, but it's not ideal. So it's like we have a certain cooling scheme that we have a series of random variables, and this variance is decreasing, and each of this kind of random variables are related.
Oh, I see. It's not just averaging because they're dependent?
For each of the random variable per se, it is averaging, but we have this kind of cooling idea that this is like a series of different random variables, and with whose like variance is decreasing, decreasing and decreasing.
Any other questions? Okay, so please thank our names. Talk is separate design.
This is me begging for an extra minute. So yes, I'm going to talk about higher momentative stabilizer states and some of the applications. And it's a joint work with David Gross and Michael Walter. So first of all, why we care about this is basically because stabilizers and equilibriums are everywhere, and from fault tolerance, quantum codes, QKD, and random benchmarking. And so it's going to be useful knowing the statistical properties are also useful for many of these tasks, and even also in near future. But unfortunately, we know very little about higher moments of a stabilizer state, except for the cases that they match the higher moments of random ordinary states. For example, we know that qubits are 3 designs, which means that if you compute a third order polynomial of random stabilizer states on n qubits, it's going to be the same as arbitrary states. And what I'm going to do in this talk, I'm going to present a geometric way to thinking about the higher moment of a stabilizer states, and basically show you how you can compute all moments of a stabilizer states. And yes, so as a motivation, I'm just going to give you a list of applications, and I'm going to tell you how it works. So first application is basically, as I promised, it's a simple formula for average of tensor powers of stabilizers. In terms of some RT operators, which are in the commutant, and I will define for you later. These are geometric objects I was talking about. A second application is basically solving an open problem in quantum property testing, which we solve the stabilizer testing. This question is that given an arbitrary state on n qubits, whether you can check that the state is close to a stabilizer, is the stabilizer or far from all stabilizers? And we can show that with 6 copies of any state, you can check that. And the last one is this exponential definity theorems. For those of you who know definity theorems, we show that if you increase the symmetry of a stabilizer state from the permutation symmetry to a natural symmetry of stabilizer states, then you can get very, very strong definity theorems. And but I will not have time to talk about these things. I will go to computing the higher moment of stabilizer states. And the key to this computation is just looking at the commutant of stabilizer states and tell you what the commutant is. Suppose that you have an n-qubit arbitrary unitary, non-Clifford unitary, and look at T tensor power. And the commutant of this unitary is all matrices M that commute with these U tensor T's for all U. And a natural candidate for an element of the commutant is just permutation of these T replicas, T tensor powers. Because if you have T replicas of your system of n qubits and T copies, unitaries are acting on rows, and these permutations are acting on columns. So these operators R pi tensor n's, which permute these things, are in the commutant. And we know that by a theorem, and in fact, these span the whole commutant. And what I'm going to do is find the commutant for the Clifford group. So we know that the Clifford group is a subgroup of the unitary groups. So the commutant of the Clifford group is going to be larger than the commutant of the Clifford group. Commutant of the Clifford group is going to be larger than the commutant of unitary group. And we know that the commutant of the unitary group is generated by permutations. So the idea is that to generalize these permutations to something which is appropriate for the Clifford group. And this is what I'm going to do in the next few slides. So first, the first step is to just write the permutation of T qubits in a nice form. What I'm going to do is to suppose that this R pi is a permutation of T qubits, and suppose that T is equal to 3, and pi is just this matrix that commutes first 2 qubits. And I can write it in this form, which is basically a resolution of identity that sends qubit 1 to qubit 2, qubit 2 to qubit 1, and qubit 3 stays the same. So this is just a permutation matrix of 3 qubits. And to generalize this, I'm going to define this subspace, T pi, which I construct in this way. I put this permutation matrix in the first block, an identity in the second block. And what I'm going to do is look at the row space of this matrix. And this is going to be a 3-dimensional subspace of this 6-dimensional space. And this R pi, this permutation matrix, can be written in terms of you choose a vector in this subspace, and if you pick the first 3 elements, and you put it in a ket, and the second 3 elements and put it in a brawl. And this is another way to write this permutation matrix. So I look at, so still just permutations. What are the properties of this matrix? First of all, any two vectors are orthogonal mod 2. So x dot x prime is 0, they're self-orthogonal. Property 2 is the number of 1s in the first 3 is equal to number of 1s in the second 3. There is stochastic. And I put a mod 4 condition, although it's correct for integers. And the last one is the dimension of this subspace is 3, is equal to T. So these are just properties of this matrix. And now the theorem is to generalize this. Instead of permutations, consider all possible subspaces that have these 3 properties. And the theorem shows that if I look at RT tensor n, they will be in the commutant of Clifford group. So instead of permutation, I use this kind of subspaces. And I define the RT operator in this form. Put the first T elements in the kit, last T elements in the bro, and they form the commutant. And that's it. Thank you. Yes?
You said 6 copies suffice for testing stabilizerness. Do you have a lower bound on how many copies would be needed? I mean,
6.
Oh, that's the tight answer.
I think so. Yes. Yes. The answer is yes, but it's not written. It's not nice. But yes.
Okay.
Yes. For if you use everything everything I described here was for qubits, but in the paper is everything for qubits for d not equal to 2. For d not equal to 2, then you can show that you can do it with 3 qubits. In some cases, you can do it with 3 copies. And 3 is optimal because qubits are 2 design. So you can't do it with 2, but with 3 you can.
And you can't do it with 5. Sure.
No.
What is your hope to use it for? Like, what's your dream application of this?
So this is a dream, because you can get so this kind of definitive theorems. So basically, you make your permutation symmetry slightly stronger. That I didn't talk about what kind of symmetry you're going to use, but the stabilized tensor powers or stabilizers satisfy this kind of stronger symmetry I didn't talk about. And then you get the definitive theorems where it's exponential in number of bits that you erase. So if you have 2 billion qubits and you just erase if you trace at 5 of them, then you get something that is exponentially close to a complex combination of stabilizer states, tensor powers of stabilizers. So that can be hopefully useful for key distribution. Yes.
Is it easy to find the subspaces?
Yes. You can find them. You can count them. And they're usually not that bad. For example, if you t equal to 3, then you can see that they're just permutations, which shows that qubits are 3 design. But the number, for example, t equal to 4, there are just something like 25, 30 of them, and they're not that bad.
Okay, let's next up again.
Zvika. Okay. Yeah.
All right. Okay. So then for our last talk, we have Zvika Brakarski.
Hey, yeah, I want to tell you about learning with errors and the Hydrol coset problem. And this is work with Kirshanova, Stille, and Wen. It was published in a conference called PKC a few months ago, which most of you probably don't attend. It's also, I guess, in the archive. But mostly, I want to sort of remind you of the connection between learning with errors and lattice problems in general and the Hydrol coset problems. So what is LWE? So it's due to Regev. And in LWE is the following computational problem. We consider a matrix A, which is n by m. M is much bigger than n. And this matrix is modulo Q. So all elements are between, say, 0 and Q minus 1. And this is a public random matrix. And now what we do is we take a random combination, random linear combination of the rows of A. We add to that some small noise, so some vector of elements where all elements are just small numbers, much smaller than Q. The result of that is some other vector. Let's call it U. And the learning with errors problem is given the matrix A and the vector U to find the coefficient S, the coefficients S. And this is a computationally hard problem. And so I didn't say what Q is. So think about Q as polynomial in N, let's say N to the 10 or something like that. And this is, as far as we know, hard also for quantum computers. And actually what Regev showed was that if you can actually solve this problem, then you can solve a large class of what's called lattice problems using quantum algorithms. Good. So what's one way that you can approach solving this problem? So given the matrix A and the vector U, you can generate the following superposition. So I can think about some. So I can take a superposition over like bits B and some vectors X, which are just n-dimensional mod Q, so similar to this S. And then I can compute X times A minus B times U. So this is something I can do given A and U. I can generate this superposition, and all of my arithmetic is modulo Q. And furthermore, rather than just computing this value, I can actually sort of truncate this value. So essentially, rather than just computing this value, I compute it and then remove all the least significant bits, like to some level. What does this mean? So notice that when I take X times A, this encoding is sort of very robust. So even if I remove some of the least significant bits, then this still uniquely determines X. And furthermore, if I add a little bit of noise, then I'm still going to be able to sort of get the same X. So if I compute this value and then measure this register, then what I'm actually going to get is, well, actually only two different values of X are going to survive. One that sort of corresponds to X times A, and one that corresponds to X times A minus U. So if I measure this register, then I'm going to get a superposition of the form 0x plus 1 X plus S, where S is exactly the secret of this LWE instance. And this is going to happen with very high probability. And if you are familiar with the dihedral coset problem, then you can see that this is very similar to like the oracle that we need that we get as an input for the dihedral coset. So if I get a lot of these, if I'm able to generate a lot of these samples, and I can do this process as many times as I want, and I run an algorithm for the dihedral coset, then I should be able to recover S. So one little subtlety here is that these sums are over vectors and not over integers as in the normal definition of the dihedral coset, but this is not such a meaningful difference here. Good. So you can see here that if you have a good enough algorithm for the dihedral coset, then you're going to get an algorithm for LWE. And this appears in our paper, but morally this should be attributed to Regev 03. So in 03, LWE did not exist yet. So what Regev showed was a connection between the dihedral coset and some other lattice problem using a much more complicated, using more complicated techniques. But essentially, this is what's going on. And this should remind you of Thomas' talk. Again, you have this 2-to-1 type function. This is actually a very similar or even identical function to the one that we use in the certifiable randomness paper, and also used in homomorphic encryption and the verifiability works of Urmila. What we see here is that solving the dihedral coset will allow you to solve LWE. But what about the other way around? Maybe the dihedral coset is a much harder problem. So what we show in this work is that what we can do is not just think about B going from 0, 1, but take B, say, 0, 1, 2, 0, 1, 2, 3, and so on. So we consider a generalized version of the dihedral coset. And this is similar to a generalization that was considered by Childs and Van Dam in 2007. And what we show is that if you consider this generalization, or even other generalizations, so you can extend this B, but you can also add weights here. You can add a weight that depends on B, and you probably can guess that the correct way to use is Gaussian weight. Then you can actually get an instance of a problem that can be shown to be equivalent to LW. You can actually go in the other way from this generalized dihedral coset instance back to LWE, which incurs a loss in parameters in both directions, but the loss in parameters is relatively modest. So what I want to tell you is that if you want to solve LWE using quantum computer, which you should want, or at least try to figure out if it's possible, then maybe you shouldn't insist on the sort of original dihedral coset problem, but rather think about more relaxed versions and see what can be done there. Thanks. Yeah.
Why? I mean, what are the indications that these are easier problems?
Just because, so this actually, you're not losing anything by trying to solve this problem because we know that it's not harder than LWE. So so at least you're not losing anything by working on this problem rather than directly on LWE.
So, and how much did you need to relax it to make the correspondence? How big does B have to get?
So essentially, it should get like it should be polynomial in n, but still a much smaller polynomial than q. So if q is n to the 10, then you need a Gaussian of width, I don't know, n cubed or something. I'm just guessing here in order to get like yeah.
So approximate shortest vector, LWE, and dihedral in coset. Can you show me the lattice of reductions? Just so I can have it straight in my
So approximate shortest, it's not exactly approximate shortest vector. It's like a slightly different, it's short independent vector. But all of those are actually equivalent under quantum reductions. With this generalized, this extended version of the dihedral coset that, with different parameters. Yeah, you lose parameters in the reduction either way. So if you do the full cycle, you got to like a worse, like an easier or harder instance of LWE than you started with.
So your paper, for instance, completed the picture, completed the cycle.
If you want, but we can't do it from the actual dihedral coset. So in a sense, we relaxed it and then, yeah, sure, yeah.
Don't you have sub-exponential algorithms for this quantum?
I was hoping for this question. I really like answering that. Yeah, so. Yeah, so I said that if you can solve the dihedral coset, then you can solve LWE, and we know that we have like the Kuperberg algorithm gives you a 2 to the square root n algorithm for the dihedral coset. So can you get a sub-exponential algorithm for LWE? The answer is no, and the answer is not like very apparent. So I think it's more apparent from our paper than from like, because in Regev's paper there's a lot of things going on. In particular, the reduction actually blows up the size of the instance. But that's not the reason why it doesn't work. The reason why it doesn't work is because with very small probability, you're actually not going to get a good. You're actually not going to get the correct superposition here. You're going to measure this, and the surrounding thing, you're going to be so close to the edge that instead of getting like both of these components, you're actually only going to get one of them. And the Kuperberg algorithm is actually very sensitive to the input distribution. So if I give you 2 to the square root n sort of samples from this superposition, and even one of them is not proper, then the algorithm is just not going to work. And this is the reason why you don't get a sub-exponential algorithm.
Okay, sorry, I just need to ask that. Do you think there should be a 2 to the square root n algorithm for an?
I have like sort of, I would not be surprised. 2 to the square root n seems like a reasonable answer for many reasons, but who's to be a prophet, right?
You do have 2 to the square root n approximation, for example, with polynomial time quantum algorithm, right? You do get.
We don't know. Currently, nothing is known. I mean, currently, we don't know how to get.
Yeah, but if you look at lattice problems, you can get
yes.
to the square root n approximation ratio with a poly type.
This is not known for general lattices. This is known for a class lattice called ID lattices. Yeah, but for general lattices, even that would be like huge. Yeah, we don't know.
Okay, let's thank all the speakers.